Everybody got really quiet all of a sudden and everybody sat down, so I guess we'll start. I'm sure we'll have a few latecomers, that's fine. Anyway, welcome to EAA Chapter 1541 and our IFR mini symposium we're going to have this morning. I know I see some unfamiliar faces. I know we have a lot of chapter members here, but I know we have a few guys from out of the area. Appreciate everybody coming out. We're going to spend the next 3 hours, hopefully not boring anybody, but we're going to get down into the weeds a little bit on some of this stuff, which I presume is why you guys are here. How many actual IFR rated pilots? Okay, so that's about half. How about VFR rated pilots? Okay, so, and that's fine because, you know, in the world of flying, in my mind anyway, a private pilot certificate is a bachelor's degree, and an IFR rating is a master's degree. So I think everybody can appreciate the amount of precision required to fly IFR. It takes a good knowledge base. It requires you to be able to communicate and fly the airplane and navigate all at the same time, and particularly for IFR, single pilot operations, it's not an easy task. So anybody who's flying IFR and actually IMC once in a while, my hats are off to you. I think it's a great skill. It really expands the utility of an airplane to have the IFR rating. So it's not for everybody, but if you're serious about flying, particularly en route, it's a good way to learn an awful lot about the system and have it used, and be able to use it to the maximum extent possible. So for this first hour, I'm going to talk about IFR procedures and how they're put together. And then the second hour, we have Casey Lyons. Okay. I know he just, oh, I'm sorry. Sorry. I looked, but I didn't see. So anyway, Casey Lyons is a longtime controller over at NorCal, and he's going to present for about an hour. And then the third hour, we're going to have basically a open forum with questions and discussion about IFR flying. And I'm hoping that we get some questions and some discussion from everybody, some experiences, some good things to do, some good things not to do during when you're flying IFR or VFR too. And if that kind of peters out, we're going to have one last scenario to discuss that we have some information for. So it just depends. But my intent is to go till noon. So we hope to fill the morning up. If you guys came out, we might as well make it worth your while. So, okay, so this is the first presentation I'll do. It's the nuts and bolts of instrument procedures, approach procedures. And just as my own background, just so you know who's talking to you, my name's Scott Thompson, and I've been flying since 1975. I'm a double I, ATP, and air traffic controller specialist, at least on paper. I started with the Flight Inspection Field Office at Sacramento in 1990. I did TERPS, procedures development using TERPS for 5 years, and then flew for those 5 years as a flight inspection co-pilot, mostly checking the procedures I developed. My area was California. We had like 2 or 3 guys who handled the whole state of California. This was back in the day before RNAVs were around, so we didn't have as much of a procedure load as they have now, so we just primarily did all the VOR, NDB, and ILS approaches. In 1995, I moved over to do full-time flight inspection as a PIC, and I spent the next, 21 years doing that. 15,000 plus flight hours, and most of that time was actually doing the flight check mission, flying primarily in the western U.S. We handled all the western states west of Colorado, also made forays into Alaska and other places as needed. But anyway, and I retired in 2021 as a manager over at the FIFO office, which is over at International Airport, still there. Thankfully, it's still there. Hopefully, it's going to be there for a while longer. And they still launch 2 or 3 airplanes every week doing flight check missions. So they're still over there. We used to do tours over there, but FAA facilities now, you can't even get in. I can't get in. I'm retired, so it's not easy. Okay, ICAO, the international definition of an instrument approach procedure is, as anybody here understands, They're used by aircraft flying in accordance with instrument flight rules and are designed to facilitate safe and efficient aircraft operations. I'm going to move the mic here a little bit. Okay, so the standard document that's used by the FAA procedures development people is known as TERPS. Everybody who flies IFR is probably familiar with that term. Somehow they get TERPS out of the name of the order, which is the United States Standard for Terminal Instrument Procedures. It doesn't make an acronym, and it also doesn't, TERPS also has en route procedures. All the airway development's all done also through criteria that's in TERPS. It's the 8260.3 order. It's available online for anybody who really wants to get into this. This is my old TERPS manual, and well used, but this is basically the size of the manual. It's like 500 or 600 pages, but it's, like I say, it's available online. And it covers the procedure development of all of these different IFR procedures. So it's precision approaches, non-precision approaches, departures, stars, en route procedures are all outlined with detailed criteria. Also covers things like visibility minimums, takeoff and departure minimums. So it covers the whole gamut. How to name procedures. It's very in-depth, and if you either have the interest or you want to put yourself to sleep, the manual is available online. There's a parallel order that goes along with it. It's 8260.58, and it kind of does the same thing for RNAV procedures. So it's providing all the criteria for how to design an RNAV procedure, and a lot of times the criteria overlaps with regular non-RNAV procedures, but it still provides all the information in that one order. Also available online if anybody wants to dig into it, why an RNAV procedure is the way it is. But for the most part, TERPS is about obstacle clearance. It's designed to set up areas that are evaluated for obstacles to allow a pilot to fly IFR without reference to the ground, just using reference to instruments, and that's pretty much the name of the game, although it is about other things too. TERPS obviously is concerned about traffic flow and other factors for operating IFR or VFR, but primarily IFR. TERPS is the United States standard for procedures, whether it's the FAA develops them, the Army, the Navy, the Air Force, any organization in the U.S. that develops procedures is going to use the TERPS manual. It's a standardized criteria, so if you fly a procedure in Alaska, it's going to be designed the same way as if you fly the procedure in Florida or Massachusetts. It's all standardized across the entire system. TERPS was the basis for what ICAO developed, the International Aviation Organization, basically developed their standards out of what the U.S. had developed for TERPS. But it's changed. They've kind of diverged in the years since, but the criteria is still similar, and U.S. criteria meets international standards. But that's where it came from. So some of the terms we're going to talk about today are obstacle evaluation areas. It's exactly what it sounds like. Required obstacle clearance on procedures for different segments. Obstacle clearance surfaces, which is primarily how climbs and descent, procedures involving climbs and descents are evaluated, and then maximum and minimum climb gradients. One thing that one of the questions about from a lot of people is, well, what if it's an emergency? What if we lose an engine? What are we getting out of TERPS? Well, you're not getting anything out of TERPS. TERPS establishes a minimum climb gradient for segments, or it may require a certain navigational capability. The expectation is the pilot can meet that. If for some reason you have an aircraft performance issue or you can't meet the climb gradient, then TERPS won't give you anything. Now, particularly in critical situations, say at Eagle in Colorado or Aspen or some other airports where it actually could be a dire emergency if you lost an engine, there are companies that will develop emergency procedures that can be flown if you lose an engine, or if you for some reason have some type of critical issue that you cannot fly the performance required to do an actual FAA procedure. And those don't use criteria. They basically set up a route that you can fly where you won't hit anything, but there's no there's no TERPS protection for those procedures. So most everybody IFR certified knows about approach procedures, but this is the gamut of procedures. You have precision approaches and non-precision approaches, and then in the middle there you have approach with vertical guidance, APV approaches, which are handled identical to precision approaches. The only difference is those three type of approaches, an LPV, LNAV, VNAV, and LDA with glide slope, don't match the exact definition that ICAO uses to define precision approaches. So they're called approach with vertical guidance here in the US. Actually, APV, approach with precision vertical, I guess that's what that stands for. There's approximately 12,500 approaches maintained by the US, by the FAA. And two items notable on here, there's about 1,680 ILS procedures, and there's 6,588 RNAV procedures. So that kind of gives you an idea of the balance. There's very few, if any, new ILS is being installed anywhere. The equipment is expensive, the maintenance on the equipment is expensive, the surveys required, and all of the other things go along with it. It's not likely you're going to see very many ILSs installed, new ILSs installed. Now the FAA is replacing older ILS equipment with new equipment, so they're still installing ILSs, but they're just basically providing a replacement equipment. Sometimes that old equipment might be repurposed to a small airport if there's a requirement, but it's, like I say, it's expensive. It's easily replaced by an RNAV approach, particularly at general aviation airports. Now we're fortunate here at Lincoln because we have an ILS. If the situation, I think they installed this ILS about 1980 or so. Well, it wouldn't be installed today. If they're looking for a place to put an ILS, it wouldn't be Lincoln. So we're fortunate to have it here. It's kind of a reliever for training that might be done in Sacramento International, and people can fly ILSs here rather than do it over there. So it's great we have one here at Lincoln, and we want to guard it judiciously. We want to make sure that we don't lose that ILS. But the RNAV, particularly the LPV approaches, can give you everything an ILS will give you, and it's much less expensive for the FAA to maintain that. It's basically a database maintenance rather than an actual facility maintenance. So this is what an FAA procedure actually looks like as far as the FAA is concerned. This is a standard form that is put together by the FAA, and this is sent to the charting agencies, whether they're FAA or JEPSON or anybody else that creates an instrument approach plate. This is the document that they're using to make that charting. And this document, because it's part of the FAR's FAR 97.33 for this procedure, which covers RNAV procedures. So I believe these are actually published in the Federal Register and become regulatory. So this is official regulatory information. That's why you can be violated for if you break minimums and stuff like that, because this is a regulatory document. So this document is laid out with information that's presented then on the approach plate. This would be all of the information on the plan view right here. Gives the different segments, altitudes, distances. Down here in this section, this is the profile area that gets on the approach plate, shows the altitudes from different fixes, particularly on the intermediate and final segments. Down here are minimums. Over here is your missed approach point, and over here is your missed approach procedure. And then down here are notes that have to be charted on the procedure. So this one is for an LA Los Angeles procedure. This is page 1 of 4 pages, so they can be long documents. But this is an FAA procedure developed by a procedure specialist. So almost all instrument approach procedures have at least 4 segments. You're going to have the initial segment, the intermediate segment, the final approach segment, and the missed approach segment. In some cases, the initial segment will be deleted if you have radar capability to vector onto a final. But in most cases, particularly if a procedure is developed for a non-radar environment, you're going to have an initial segment. So all of these different segments have specific shapes. They're trapezoidal, This is the initial area here. This is the intermediate segment where it narrows down. You have the final approach segment here, and then the missed approach segment here. And each of these segments has criteria specifically designed that's available in TERPS as to how these areas are designed. And the only reason these areas are set up the way they are is to do an obstacle evaluation. So the obstacle evaluation areas for the initial segment is contained inside the trapezoid. Center line has a certain level of required obstacle clearance, and then the secondary areas are out on the edges, and they have a reduced rock requirement the further you go from the edge of the primary area. From the side, you can see basically at the profile view. So we're going to talk a little bit more about each of these segments, at least for a minute or two. So I talked about rock, required obstacle clearance. So each of the segments has an assigned rock value. For example, in a feeder segment, the feeder segment would be a transition area from an en route navigate or an en route fix into the initial approach fix. So it's basically an airway that's established just to connect the approach to the en route structure. Not all approaches have feeders, but if it does, it's going to use the same en route criteria, the rock value for a feeder. Initial segment can be a straight segment, a DME arc, a procedure turn, or a holding pattern. Once again, the criteria is all outlined in depth, in excruciating detail in TERPS on how to put these together. Intermediate segment, final segment. Most final segments have 250-foot rock for a non-precision approach. The exception is an NDB approach, which gets a higher value of rock for obvious reasons. And then for a precision approach, the obstacle clearance surface has to be clear. We'll talk more about that in a few minutes. And the same with the missed approach segment. You have a surface that has to be clear, and missed approach holding patterns, 1,000 foot of a rock in the holding pattern. And then circling, we have a circle maneuver. You provide at least 300 feet of rock around in the circling area. I'll move this again, sorry. Okay, so let's talk about some of these segments. We'll start with the missed approach. We'll start with where you end on a procedure. So every standard instrument approach procedure has a missed approach point, and it has a missed approach procedure. Non-precision approach points are, as everybody who flies IFR understands, could be a timing table, which allows you to determine your distance from the final approach fix using a timed table based on ground speed. Not particularly accurate, but that's one of the methods to identify a missed approach point. A DME fix, which is much more accurate, actual facility overflight, or a combination of a timing table and a DME fix, and finally a waypoint for an RNAV procedure. For a precision approach, you have a decision altitude that is established as your missed approach point. So in that case, it's not a geographical point, it's a point where you're descending on the glide slope and you reach an altitude that then determines if you can continue to land or if you're going to execute a missed approach. So these missed approach segments also have these complicated trapezoids that are developed using TERPS criteria. And as you can see, if you can see some of this, how they draw this stuff, it's very complicated. But what it provides is, in this case, the runway is right here, the missed approach point is back here, and it provides a routing to safely climb back up into the en route structure. Now, the non-precision missed approach is fairly straightforward. You'll have your minimum descent altitude on your final segment to your missed approach point, and then from that point, there is a imaginary 40-to-1 missed approach surface that starts at that missed approach point and climbs along the missed approach flight path. So that 40-to-1 can't be penetrated with an obstacle, an antenna or terrain. So if a terrain or an obstacle does penetrate the missed approach surface, then it has to be addressed either by changing the missed approach route or raising the MDA in order to get the starting point of the 40-to-1 surface high enough to clear the obstacle. So a lot of times you look at an approach and you can't understand why the MDA is so high. It doesn't make any sense. Well, a lot of times it's because there's obstacles in the missed approach segment, and they've had to raise the MDA in order to provide a safe climb over the obstacles if you have to miss the approach. Precision missed approach is a little bit more complicated because the precision approaches are more complicated, but basically you have the same type of thing. The difference is on a precision approach, because your missed approach point is the decision altitude, the aircraft is in a descent on the glide path. Well, if you decide to miss the approach, you're not going to immediately start climbing. You have to go, there's a transition area where you continue descending below the decision altitude as you clean up the airplane and get ready to fly the missed. And that's accommodated for in a precision approach, missed approach procedure, where you have this is the glide path here, and then you descend below the decision altitude, start your climb, and then eventually you rejoin that 40-to-1 surface. So not a big deal, but it's something to know that if you descend below the decision altitude, transitioning into a missed approach, you're still protected from obstacles. So as I mentioned, the missed approach obstacle clearance surface is a 40-to-1 slope, and that equates to 152 feet per nautical mile, so it's a fairly shallow climb gradient. That's the obstacle surface that climbs. The expected standard is that aircraft will climb at 200 feet per nautical mile to fly the missed approach, which equates to 400 feet per minute ground speed if you're flying at 120 knots. If you're flying at 90 knots, it'd be 300 feet. If you're flying at 180 knots, it's going to be, 600 feet? So the main thing that you need to know is if you're flying your Cessna 150 at Reno on a hot day, you're expected to be able to fly the missed approach procedure. So it doesn't usually come into planning. You're flying Bonanzas, you're flying RV-10s, you have the performance, but it's something to consider that this is the expectation. And if you're flying single engine in a twin engine airplane, once again, if you can't climb, then you're not going to get any obstacle protection by flying the procedure. So this is the standard that's expected, 200 feet per nautical mile. Another way to get around an obstacle in the missed approach segment is actually to require a higher climb gradient in the missed. And that way your obstacle surface climbs faster and therefore you can clear out obstacles. But if they do that, then they have to also provide a set of minimums where you will be able to climb at the standard climb gradient. And this is an example at Yakima up in Washington, where you'll have a hashtag on the lowest set of minimums here of 1268 your decision altitude, but in order to fly those minimums, you have to fly this restriction here. You're required to have a minimum climb gradient of 275 per nautical mile to 3,600. So if you don't have that capability, then you use the second set of ILS minimums, which is 445 feet higher, 1713 for your decision altitude, and that is just for missed approach obstacles. They'll publish two sets of minimums sometimes, just to give aircraft a lower set of minimums for the approach itself. So we're going to get into final approach segments now. So we're doing that time. So the non-precision approach segment is much like all of the other segments on a procedure, all the initial, intermediate. You have level surfaces that are evaluated. And for example, in this missed approach, you have your final approach fix, you have a step down fix, and then you have your missed approach point over here. So these clearance areas, these obstacle evaluation areas are level. And basically, the minimum descent altitude is just established based on the highest obstacle in the area increased by the rock value to provide you with the minimum descent altitude. So this is the old dive and drive type approach where you would cross the final approach fix and then drop as quickly as you can to the minimum descent altitude for that segment, and then you would descend very quickly to the next altitude, and then you continue the approach. Now, that's not the way you have to fly the approach, but that's the old-fashioned way. Now they've provided some other information that will allow you to make a stabilized approach. But the basic requirement for a non-precision is just this. They're level planes and they're evaluated simply based on the obstacles, and then they'll publish a minimum altitude for each of the segments. This is a profile or a straight-on view of what the rock looks like. So on a non-precision approach, it normally is 250 feet, and you have the primary area that goes out, and then secondary areas that slope up at a specified slope to reach the edge of the secondary area. Now, this rock adjustment, on final segments, the required obstacle clearance can be increased. There can be an adjustment made for any number of reasons. Remote altimeter, you might have an excessive length of the segment, and there's like 10 or 15 different required adjustments that will be added onto the rock value in order to provide the minimum safe altitude for that segment. So this is a VOR trapezoid for a VOR approach, and the reason, why I'll just ask, why does it narrow up here? Here's the facility. This is 30 miles out. Why do you suppose this narrows up? Anybody?
Yeah, the beat from the VOR.
Yeah, the VOR signal is more accurate the closer you get to the station. So the trapezoid is designed to accommodate that. The closer you get to the VOR, the more accurate your navigation guidance is on your CDI needle, and therefore the smaller the area for the obstacle evaluation that's required. So this is an example. This is normal standard trapezoid is out to 30 miles, and at 30 miles, the primary area is 2.5 miles each side of center line, and 1 nautical mile of a secondary area. Now, at the facility itself, it's only 1 mile wide each side of center line. So it's still a big area, but anybody who's flown VOR, sometimes you need a big area. So, but when a procedure is actually developed, a VOR approach is actually developed, they will take only a slice of that trapezoid in order to create the procedure. So, for example, in this case, you're flying away from a VOR. Here's a facility, you're flying toward the missed approach point. And in this area out here, it's going to be your intermediate segment. But the actual part of the missed approach, or the final trapezoid that's used, is just the part between the final approach fix and the missed approach point. So they just overlay the pertinent part of that trapezoid to make the procedure. In this case, you're flying toward the facility, here's your final approach fix, so they're only using that part of the trapezoid. And then in this case, your facility is off the airport, you're flying toward the facility, and they're using that part of the trapezoid. So it just depends on how the procedure is designed, but the trapezoid is standard, and then it's just applied, the part of it that they needed for the procedure itself is applied. NDB final approach segments are much larger for a good reason. Anybody who's flown an NDB approach, sometimes your needle is going 10 degrees each side of center line. This is not the most accurate navigation aid you're ever going to find, but that is basically, there's only, 176 NDB approaches that remain. So this slide can probably be pulled off pretty quickly. It's not that many NDB approaches. So this is a RNAV, an LNAV final. This is a non-precision LNAV final using GPS. And the basic trapezoid for the final segment is rectangular rather than narrowing up. Anybody guess why that is? For the same reason that the VOR trapezoid narrowed, with an LNAV final segment, the course guidance is constant. Your GPS navigator will establish for a normal LNAV approach, it'll establish a 0.3 nautical mile course deviation. So if you're flying a final segment on a GPS approach, if you have a full scale deflection, you're at least 0.3 of a mile from the center line of the approach. You could be more, but you're at least 0.3 of a mile. But that's going to be true for the whole segment. Your navigation accuracy of your equipment does not change. It's going to stay constant. So therefore, here's your final approach fix. here's your missed approach point, and the basic trapezoid is rectangular. Now, you'll notice here on this trap, the width of the primary area each side of center line is 0.6 of a mile. So they give you a lot of room to get off course. Not that you want to get off course, but you'll have full-scale deflection halfway out, and then you have another 0.3 of a mile beyond that. And then beyond that, the second area is another 0.3 of a mile. So there's a lot of room for slop here, but obviously you don't want to be sloppy. You want to be on center line. But anyway, so the LNAV final segments presume constant needle accuracy. It's not going to change. Now, where it does change is the intermediate segment. It's 1 mile sensitivity on your needle. So these areas here where it ramps down to 1 mile, which is why they're drawn like this. But once you get into the final segment, it's going to be rectangular. And this, at the other end of the missed approach, your precision on your needle ramps back up again, and that's why they have an expanding area here. So now let's talk about precision finals, and they're a lot more complicated. This would be a ILS trapezoid for a localizer, and you'll notice it's much narrower up here. These numbers down here are the width of the areas, but there's 3 different obstacle surfaces that are evaluated, and they're all sloping. In other words, you're on a glide slope. Your obstacle clearance varies depending on the distance from the runway. So there's 3 areas that are looked at. You have a W surface that's right on the center line, goes all the way out to the final approach fix, and then you have an X surface beside that, and then a Y surface beside that. And every one of these has different requirements depending on how far you are out from the runway threshold. So here at threshold, your W surface is 400 feet wide each side of center line, but out at 50,000 feet, it's 2,200 feet wide. So it narrows down. Once again, the reason it narrows down is because the localizer gets much more accurate when you're closer to the antenna. So therefore, you're allowed, the trapezoid reduce, the area that's evaluated for the obstacles are much reduced based on how far you are from the runway. This is a side view. Basically, you're looking at the same thing. You have the obstacle clearance surface here, and then you have your actual aircraft on a glide path here. And the rock value that's established will be reduced the closer you get to the runway. Now, normally outside the decision altitude, you won't have any penetrations of that obstacle clearance surface. So outside the DA, you should be clear. This is another view. Here's your surfaces here, your W, X, and Y surfaces here. This is a transition area here, flying into the missed approach. Like I said, the formulas used to calculate the actual elevation of this obstacle clearance surface are pretty complex. I would be willing to offer anybody the opportunity to do a calculation of the obstacle clearance surface based on that formula right there. So when I did TERPS, when I did TERPS back in the early 90s, the criteria is much simpler. But as the years have gone by, 2 things have happened. The main thing that's happened is most of the procedures are now done using automation. The basic procedures built using automation. And nowadays, there's extremely accurate terrain databases and obstacle databases that can be used to do this analysis. So once they have the basic data in there, they'll run all of the obstacles and all the terrain through the computer to determine whether or not the obstacle clearances are clear. So that's the basic reason why these formulas are so complicated, but obviously they're also fine-tuned the criteria to take advantage of that to make sure that they're getting the most efficient obstacle clearance, not overdoing it or not underdoing it. So anyway, it's very complicated, but this is how the elevation of the obstacle clearance surface is made. So we'll talk about RNAV finals here for a moment, LPV and LP. So the LPV is localizer performance plus vertical. And LP and LPV approaches require WAS and a wide area augmentation system enhancement on the positioning of the aircraft. You have to have an approved GPS navigator that can incorporate WAS into the navigation solution. And but the important thing to know here is that the LPV is designed to mimic the sensitivity of a localizer and a glide path. So if you're used to flying an ILS and you go fly an LPV, you're going to see very similar CDI deflections on both your centerline needle and your glide path. So that's designed that way specifically for a reason. They could set it up any way they wanted, but it's designed, as the name says, it's localizer performance. So therefore, okay, to establish that data, every LPV approach and every LP approach will have what's called a final approach segment data block that encompasses all of the information that your navigator, your GPS navigator requires to create that localizer and glide path type signal. So there's a lot of different data in here that's all combined. These are basically the important ones. But the first three here establish your localizer, and then the bottom four here establish your glide slope. And then for protection, there is a cyclic redundancy check that's done with the data, which anybody who's familiar with databases probably understands what that is more than I do. But basically, a calculation using an algorithm is made to evaluate all this data, plug it through a formula, and then you come up with the remainder code here. And when your navigator makes this calculation, it will compare this CRC remainder with what is in the database. And if they don't match, you have corrupt data somewhere and your LPV approach will be flagged off. You can't fly it because there's a data error somewhere. It's expecting this, it's getting something else, therefore it's not a valid procedure. So every time the procedure is amended, or any of this information is amended, doesn't matter by how much, it will create a new remainder, and then that will be a new addition to your database. It'll replace the old procedure when you update your database. Briefly, we'll talk about LNAV VNAV, which is probably a poor man's LPV approach. But the important thing to know about an LNAV VNAV, well, there's two things. First of all, the LNAV portion is also rectangular. So the trapezoid that's evaluated is the same as an LNAV trapezoid. It doesn't narrow up as you get to the runway threshold because it's using an LNAV signal and not an LPV signal. The second thing is most, not all, but most LNAV VNAVs are flown using baro VNAV, which means your altimetry becomes very important. If your altimeter setting is wrong or the temperature is much higher or lower, then you can have issues with the glide path. And the evaluation is made, the slope will actually change. Your flight path will actually change based on temperature. So it's evaluated by the TERPS specialist through a temperature range to make sure that you have sufficient obstacle clearance regardless of the temperature. And that will generate a note like we have at Lincoln. The first highlighted note for uncompensated baro VNAV systems, LNAV VNAV is NA below 15, minus 15, or above 48 degrees. And every LNAV VNAV approach will have this note on there. Maybe not the same temperatures, but it's basically restricting users to those temperatures. Now, minus 15 is about 5 degrees Fahrenheit. So if we have that here at Lincoln, nobody's gonna be flying. 48 degrees centigrade is about 118 degrees. So there's potentially in the summer we could have that. But like I say, I'm curious, who's flown an LNAV VNAV in actual conditions? Anybody? 2, 3, I have a couple, 4. Okay, so it's a procedure, but now an LNAV VNAV can also use a WAS signal to generate your glide slope, but you have to know what you have and what you're getting. If you're flying a GPS that has LPV capability, there's a good chance you're getting a WAS enhanced glide slope on an LNAV VNAV. If you're flying a regular old LNAV approach, then, LNAV capability, you may not have. If your box allows you to fly LNAV VNAV, then you need to figure out what you're getting, what is generating your glide slope. That's the bottom line. So that gets us to talk about databases for a moment. These IFR databases are essential when you're flying an RNAV approach on IFR conditions, or just flying IFR period. I've heard stories of guys loading these things into their iPad and trying to fly them off of that. Not a good idea. Every one of these legs has coding in the database that determines your sensitivity of your needle, the type of overflight of fixes, whether it's a flyover or a flyby. So the database is essential to get an accurate approach. And particularly on an LPV, you need to have a approved GPS navigator with a current database to fly. That just goes without saying, but it's important to know. Okay, so we've talked a lot about the different segments. I wanted to kind of hit a couple other points here before we wrap it up for this first hour. So there's a misconception here with vertical descent angles. I thought I'd just talk about this for a minute. So how many IFR pilots or anybody aware of these VDAs on the procedures? They're right here on a FAA chart. They're right here on a Jepson chart. Anybody aware of those? You guys may get a snowflake on your GPS navigator that shows you the glide path that you're getting off of that. Is that correct? Everybody seeing that? They're flying the approaches. It's an LNAV approach, but you get a snowflake or some type of glide slope indication. Is there anybody who's seen that when you fly? Okay. So when you're flying an LNAV approach, you're given vertical guidance, advisory glide slope on some approaches, and your navigator will provide that information. You activate your LNAV approach, it may provide vertical guidance also, but the thing that needs to be understood is that is not an actual glide slope. A VDA is calculated for every single non-precision approach. It basically establishes the descent gradient on the final segment. So depending on the category of aircraft, you have different angles that are allowed. I think the maximum angle for Cat A was like 3.77 degrees. For Cat D, I think it's 3.50 degrees. So that vertical angle is calculated by the TERPS specialist. It becomes important to maintain the criteria. But Navigator will a lot of times take the final approach fix altitude, and it will take the threshold crossing height information, and it will mathematically create this glide path. And if you get one, it is an advisory glide path, and you sometimes will get a glide slope type symbol will be provided to the pilot on his flight display. Now, the FAA, in many cases, will not publish this information. They don't want it used for that purpose, but avionics systems will still generate a glide path symbol in a lot of cases. I've seen systems where there's no VDA published because the FAA doesn't want you to use it, but the avionics still create it because it's automatically set to take your final approach fix altitude and your TCH and create a glide path for you. But it's important to know that the highlighted areas explain it a bit more. This is out of the AIM. The last sentence is probably the most important one. The publication of a VDA does not make the approach an APV procedure, since it must still be flown to an MDA and has not been evaluated as a glide path. So you need to make sure that you're not sucked into an idea that you're flying a glide path if you get vertical navigation on an LNAV approach. There's no obstacle clearance provided by a VDA below MDA, regardless of any glide slope indications you might have. You can be flying below the MDA, you're on a glide path, you're doing this at night, and there could be trees in front of you you're not seeing. So you don't want to assume the safety of a VDA when you're flying below MDA. Does that make sense? But there is some protection afforded on every precision or non-precision approach because there's a visual area that's looked at by the TERPS specialist. Everybody needs to understand, and I'm sure does understand, whenever you're operating below decision altitude or an MDA, you're operating visually. You're not longer necessarily getting obstacle protection. So, but this visual area is evaluated. For a non-precision approach, it's usually evaluated between the VDP on the approach. We haven't talked about that, but most IFR pilots know what the VDP is, or the decision altitude on a precision approach, and it's evaluated between those points of the runway threshold. And it goes out, depending on what type of approaches, it'll go out to the final approach fix, or it just depends. But there's two obstacle surfaces that are evaluated there. There's a 20-to-1 slope that is evaluated and a 34-to-1 slope. And there can be penetrations of those surfaces. There's no protection afforded other than if you have a penetration of a 34-to-1 surface, the minimum visibility is 3/4 of a mile in order to provide the pilot with the ability visually to acquire the obstacle. If you have 20-to-1 penetration, which is equivalent to 2.86 degrees, that slope, you're limited to 1 mile visibility. And if the obstacle penetration is unlit, if it's a tree or something out there that's not terrain, then you'll have an NA at night note on the procedure because visually you can't acquire the obstacle because it's dark and it's not lit. And then you'll have a note like here at the bottom, a straight in runway XX at night operational VGSI is required, remain on or above the VGS glide path until threshold. So that's what provides you with some protection. Now, a VGSI in general, for both VFR and IFR pilots, normally provides obstacle protection for a 4-light PAPI system or a VASI system. You'll normally have 4 miles from the threshold and 10 degrees each side of center line. That's the usable area of the PAPI, and it's evaluated for obstacles. So if you have a VGSI on that runway, then you have some obstacle protection as long as you stay on or above the glide path. Now, I'll note that a lot of VGSIs, like the one at Auburn, for example, the PAPIs are restricted beyond a certain distance, certain degree offset because of terrain or something. So it's not always going to be 10 degrees of center line. It's not always going to be 4 miles. Any restrictions to a VGSI system is going to be published in the chart supplement. But I'll reiterate, this is out of the AIM. It is the responsibility of the pilot to visually acquire and avoid obstacles below the MDA and DA during a transition to landing. Once again, it is a visual maneuver, and that's why visibility minimums are established that allow you to see the obstacles that you're supposed to see and avoid. You don't want to make the assumption that if you're always on the glide path, you get adequate obstacle protection. But where this is particularly important is on a circling maneuver where you have a real high height above airport on your circling minimum, say 1,000 feet above the airport, which is not uncommon, particularly if the runways are not aligned to the approach course. You might have a 1,000 or 1,500 foot HAA on the approach. And what needs to be understood also with that is once you descend below MDA, okay, so the requirements are you can't operate below MDA on a circle maneuver unless you can make a normal approach and land, right? Okay, that's basic. If you have a 1,500 foot HAA and you're flying downwind, you're going to be hard pressed to get down to a normal landing if you don't descend while you're on the downwind leg. But if you descend below the MDA before you're circling MDA on the downwind leg, you're on your own. There's no obstacle protection afforded at all. So you need to keep that in mind, particularly in low vis or at night. If you fly into some airports, there's terrain around the airport. The MDA for the circling is based on you staying above at that altitude until you can visually make a normal land to the airport. So once you get into the area where the VGSI is available, then you know you have protection for obstacles. But if you're 1,500 feet and you're waiting to turn you turn base and then you're turning final at 1,500 feet, you may not be able to make the runway with a normal approach. So it's just something to keep in mind if you're flying circling maneuvers at night at airports that are challenging or you're not familiar with. So I'm going to take just a few minutes here. This is kind of pulling it all together, all the information that I've presented here. This is the RNAV procedure for 25 right at Los Angeles. This is the plate. This is the procedure that the plate is published off of. We talked about this already. The FAA TERPS specialist puts together a data record for this approach that basically summarizes all of the information that he or she used to create the procedure. So this data record is not published, it's not available outside the FAA because it's an internal document, but it just provides a summary. So all of your approach segments are listed here, and then from and to are here. The obstruction that was identified for a particular segment is on this column. The lat longs for that obstacle are over here, and then the elevation of the obstacle is in this column, the required obstacle clearance in this column, and any adjustments that are required to that rock value to result in minimum altitude. So this is just a thumbnail sketch of the procedure, and it provides the information to the pilot, or to the charting, to the FAA itself about how the procedure was built. This is the overlay of the whole approach on a sectional type chart, showing all the segments. So here we have several initial segments that are coming in from the east, and they blended together. This is also initial segment all the way up to here. Your intermediate approach fix is here. This is your intermediate segment here. Your final segment, missed approach segment that comes out to this point here where there's a missed approach holding pattern. So all of the obstacles are noted on an index here and numbered. For a quick reference, this is primarily a flight check chart that's used in the cockpit when obstacles are being evaluated. Not that a flight check pilot will look for every exact obstacle, but what they're primarily looking for are obstacles that are higher than their actual controlling obstacle, looking for antennas or buildings or trees or something that are out there that nobody is aware of. Here's the final segment for that same procedure. This is the LNAV final. Once again, it's a rectangular trapezoid because of the constant sensitivity of your navigation needle. But take a look here at the end of the approach, how wide the area is. It's 0.6 of a mile each side of center line to the primary areas, and then compare that with the LPV final, which is the next slide, how much narrower that is. This would be the same type of trap used for the ILS also, but it allows obviously much smaller obstacle evaluation areas, and it also provides the glide slope for the pilot to fly it. So that's why it's so much different. But the same thing here, you have controlling obstacles listed here. In this case, the LPV vinyl is approach surface clear, ASC. So there's no penetrations in that surface, so therefore it's just noted on the chart that way. So I'll quickly talk about RNP approaches. Has anybody flown an RNP approach? Airline pilot? Yeah, okay. So that's the only guys who are going to fly RNP approaches. Are going to be primarily, I can't say only, there's always exceptions, but waivers are available. But RNP is basically, it comes at navigation from the other end. Basically, the FAA says to the airframe manufacturer and the avionics manufacturers, you give us what your airplane can navigate to, whether it's using a blend of inertial or GPS or VOR triangulation or a DME triangulation, whatever your aircraft can get in accuracy for navigation, then there's a value of that assigned, and then the airframe is approved for that level of accuracy. The pilots receive special training to fly those approaches, and it basically leaves it to the operator. Can you fly the approach? Is your equipment good enough to fly the approach? There's no requirements for equipment on the approach itself. This is an example of one RNP approach at Palm Springs. And you notice up here, it's an RNAV RNP. The standard RNAV is a GPS type approach, which means it's based on GPS. In this case, it's based on required navigation performance. And down here, you have the requirements for two different levels of minimums. If you have RMP of 0.17, you have one decision altitude. If your RMP value is 0.30, you have another one. But this basically establishes, in this case, it's almost a 360-degree overhead approach. Here's your initial approach fix. You have a curved segments and also descent paths on those segments to bring you to the runway threshold. So pilot would fly that path to get to the runway. Okay, with that, we have a few minutes for questions, although we'll have more time for questions in the third hour. But this is my baby. I got to fly this for 21 years. FAA Flight Check Learjet. Since retired, unfortunately, but that was my fun airplane to fly. But any questions right off the bat, really quickly? Wow, I either stunned you or you're so bored you're not paying any more attention. Oh, we got one question.
So the current generation of, for example, Garmin Navigators offers visual approaches. And it seems to be a standard kind of, it creates a reference point 3 miles from the runway threshold. And then, it's, the question is, does the FAA participate in any way, shape, or form of saying something might be wrong with that?
Not that I'm aware of. I don't.
Or you should be able to trust it because it's your bailiwick anyway because it's a visual approach. Yeah, it's a visual approach. The manufacturer, the avionics manufacturer, is putting some helpful assistance in there. But the only visual approaches that the FAA pays attention to from the TERPS background is a charted visual approach. And you have a few of them, like down in San Jose, I know there's a charted visual approach procedure. Other airports, basically it outlines a visual approach for a pilot. If he's cleared for that visual approach, he's expected to overfly those waypoint or those ground points to fly his path to the runway. But if the manufacturer decides to put some type of pilot assistance feature in there, a nav aid, it's not looked at by the FAA. Yes?
Yeah, I'm starting to see a lot more of the RNAVs where the advisory visual guidance is available on my GPS navigator, and my autopilot flies it wonderfully, and it seems to take the workload off, but I stick to the NDA.
Yes.
So is there any issue allowing for that glide slope? Is that going to give you the obstacle clearance as long as you maintain that NDA? And then
As long as you stay above the MDA on a non-precision, you're getting obstacle clearance provided by the procedure.
it just seems to reduce the workload.
It does, and the thing, when they first started putting these MDAs into the procedures, or these VDAs, we would go out and flight check them, and we basically, we were doing an advisory check. It's not a required check, because it's not, the assumption is the pilot will operate above MDA until he's visually able to land at the airport. But we have situations where you might have trees, really high trees at the approach end, and the VDA would actually fly the airplane right through those trees. And if you're flying at night, you're going to have a problem. And there's been at least 1 or 2 accidents where that was what was going on. Now, what the FAA does now is, if there's no criteria that specifies it, but if a flight check pilot is flying a VDA and they see an obstacle that's prominent and it could cause a problem, they will have a note added to the chart. It says basically, there's no VDA published because there's obstacles on final. Okay, but there's no requirement, that there's no criteria evaluated. It's more of a flight check pilot says, okay, that might be a problem. We're not going to chart a VDA because of it. But that's the extent of the analysis. And like I say, once you're operating below VDA on an approach, you're on your own. I'm sorry, once you're operating below MDA on an approach, you're on your own. Okay, so it's 9:32. At 9:45, we're going to have Casey do a presentation.